Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you.
Bismillahirrahmanirrahim. Welcome back. Problem 38.6. So the statement is that sigma allowable is 160 megapascal, maximum allowable shearing stress is 100 megapascal. So you have to select the most economical wide-flange shape that should be used to support the loading shown. So this is the loading shown on overhanging beam. Clear? So you have to select the most economical wide-flange beam for allowable stress and allowable normal stress and shearing stress. Also find the value expected for maximum bending stress and maximum shearing stress and the principal stress at the junction of flange and web of the selected beam. So this is the given data. I have written them and we have to find the most economical wide-flange shape, and in part B, maximum bending stress, maximum shear stress and principal stress at the junction of web and beam. So first of all, you have to find the reaction forces at point B and C. For that we have to remove these reactions and we will give the forces. Let this force is RB. Clear? And this force which is acting, and it will acting downward. Why? Because you can see this force is upward, so it will be downward, and again this force will be upward and downward in order to bring this beam in equilibrium condition. So we will apply the equilibrium condition, that sum of all movement about any point. So here we are going to take movement about point C. It must be equal to 0, taking the counterclockwise movement as positive. So you can see the movement about point C is due to this force which is 275 and the perpendicular distance is 1.5 into 1.5 plus 3.6, which is equal to 5.1 meter. The second force, as it is producing counterclockwise, so it will be positive. The second force which produce movement about point C is RB, and it is producing a clockwise, so it will be negative, and it will be RB into 3.6. The third force which produce the movement about point C is this 275 into 1.5, and again it is producing counterclockwise, so it will be positive. So 275 into 1.5, their sum must be equal to 0. So when you calculate it, you will get RB will be equal to 504.17 kilonewton. Again this RB is 504.17, so you can see this force 275 is downward, this is upward. Clear? So it cancels. So for body to be in equilibrium, this RB should be equal to RC, but RC should be downward. So we conclude that RC is equal to minus 504.17 kilonewton. Now the next step, in order to find the most economical beam, is to find most economical beam. So you have to find the section modulus, because you know that maximum stress is equal to maximum bending moment divided by section modulus. Or you can see, we can also write it as, if you have allowable stress, so allowable stress is equal to maximum bending moment divided by minimum section modulus that should bear the allowable stresses. So here you will have to find the maximum bending moment for the beam. So we will draw this beam. Let me draw it first. This is the beam. Clear? And the loading that is shown over the beam, this is 275 kilonewton. At this point D, there is again 275 kilonewton. There. So this is point A, this is point D. At point C, this is point C, and this is point B. So at point B, the force is again RB, and at point C the load is downward, which is RC. The distance between them is shown over here. You can see this distance is 1.5 meter. This distance between B and C is 3.6 meter, and again this distance is 1.5 meter. So we will draw the shear force and bending moment diagram. I will show you how to find it. So we have to draw the lines from these edges, and similarly a second line from this end there. Okay, so we will start from for the shear force. So you can see this will be 0, clear, and this will be 0 point or A point. So you can see at point A we have the force that is 275 and it is downward. So you can take this one as 50. You can choose your own scale as well. So this is 100, this will be 150, this will be 200. Similarly, this will be 300, 250, this will be 300. So you can see at point A we have 275, so 275 will be lie at the midpoint. Similarly, between point A and B we do not okay, so this force is downward, so we will go downward. So 1 2 3 4 5, so 1 2 3 4 5, and this will be downward. So this value is minus 275. So you can see from point A, this is point B, this is point C, and this is point D, and this point is point A. So from A to B we can see there is no any other force, so shear force will remain the same till point B. So you can draw a horizontal line as well, clear. Now at point B there is a force that is 504, clear, and that is upward. So 504 minus 275 will yield you 229. So 229 will lie over somewhere here, clear, so it will be here. So I will draw a line, vertical line from this point, so it will be this point. Again from B to C there is no load, so the shear force will remain constant between point B to C. But at C you can see there is a force that is minus 504 and it is downward. So 229 minus 504 will yield you 275. So again you have to go to 275, and 275 is the same point. So you have to go downward till this point. Okay. Now again you can see that from C to D there is no force, so it will again a straight line. So this is the shear force diagram for the beam. Now we will draw the bending moment diagram. Again for bending moment diagram you have to take the horizontal line, clear. So here you will draw the bending moment, and that bending moment will be in kilonewton into meter. This shear force was in kilonewton because the value was in kilonewton. Now you can check that the area under this portion AB for portion AB in the area under the shear force will give you the bending moment. So what is, as it is rectangular, so its area will be minus 275 into 1.5, which will give you moment will be between A B will be equal to minus 275 into 1.5, which will yield you minus 412.5 kilonewton into meter. Again you have to take appropriate scale, clear. So let one division is 100, so it will be plus 100, 200 and 300. Similarly here it will be minus 100, 2, 3 and 4. So we have to plot 412. So this is 100, 2, 3, 4 and 412 will be somewhere here. Clear? But it will be at point B. So at point B the moment will be this one. So this is minus 412.5. Clear? Now again the area between B and C, the portion between B and C and area under this shear force will give you the bending moment. Clear? And you can check that this area will be again equal to this force, which is 229. I will write it here. This point here force was 229.17. So 229.17 multiplied by this 3.6 will give you the moment. But this moment is positive, and here total moment will be this moment minus this moment, and that will give you point C will be equal to minus 275 into 1.5, which is minus 412.5 plus this 229.17 into 3.6, and it will give you 412.5. Okay, so we will plot 412.5, so it will be 400 and 412 will be somewhere here. So we will get this, and this point is 412.5 kilonewton. And similarly at point C the shear force will be bending moment will be 0. So now you can join these points. So this point to this point it will be this, and again from here you will get this, and if you join this point, so you will get the bending moment for the above loading. So from here we can conclude that the maximum shear force is again 275 kilonewton, and from here you can see that maximum bending moment is 412.5 into kilonewton into meter. Now you have this, since you know that sigma allowable is equal to maximum bending moment divided by minimum section modulus, so you can get minimum section modulus is equal to sigma bending moment maximum divided by sigma allowable. So bending moment maximum is 412.5 into 10 to the power 3 divided by sigma allowable was 160 megapascal. So 160 into 10 to the power 6. So you will get S minimum will be equal to 2578 into 10 to the power minus 6 square cubic meter. So again in Appendix C we have the values in cubic millimeter. So we will convert 2578 into 10 to the power 3 cubic millimeter. Okay, so now we will go to the Appendix C of book. I will show you 2578. So you can see here 2578. We cannot use this 257 because it is less than. We can use 2578. We can use W760. You can see here we can use this value 4410, which is greater than 2578. Again we can use this value, we can use these values. So I have summarized these values which are nearest to this. I will write over here. So we have shape and we have section modulus Sx or S minimum, which is 10 to the power 3 cubic millimeter. So one we have W760 by 147 and it's having 4410 into 10 to the power 3. The second W wide flange is W690 by 125 and its section modulus is 3490. The third is 4530 multiplied by 150 and its section modulus is 3720. The fourth one is W460 by 158 and its section modulus is 3340. And the fifth one is W360 by 216 and its section modulus is 1300. So you can see your minimum requirement is 2578, clear, and these are the values which are greater than this, clear. So now you have to select the most economical. So you can see all having this having weight 147 kg per meter, this is 125, 150, 158, 216. So we will select this beam. We will select this beam for above loading. Select this wide flange, and that will be safe for this above given loading 690 by 125. So this is the answer of part A. Now we will move toward part B, and in part B it is given that you have to find sigma m, and we know that sigma m is equal to, or sigma m means sigma maximum, so it will be maximum bending moment divided by section modulus. So maximum bending moment was 412.5 into 10 to the power 3 kilonewton into meter, and section modulus of this is 3490 into 10 to the power 3. So when you calculate it, you will get sigma maximum or maximum bending stress, which is 118.19 megapascal. Now for maximum shear stress, so maximum shear stress is equal to V max divided by area of web, clear. So this maximum shearing stress was from here is 275 kilonewton. So 275 into 10 to the power 3 divided by area of web, which is given to height of the beam. Now 690 by 125. So from appendix 690 by 125, you can see height is 254 and the thickness of web is 11.4. So you can, height was height was, let me check it again. Height was this, height is 678 millimeter, clear, and thickness is 11.5. So 678 millimeter, so it will be 10 to the power minus 3 into thickness of web is 11.7 millimeter into 10 to the power minus 3. So when you calculate it, this maximum shearing stress will be 34.66 megapascal. Now the third part was to find the principal stress. So for principal stress, we know that we need at the junction of flange and beam, this is flange and web, clear. So you can see this, this is the total height, which is again here 678. So if you divide it, so it will give you the center. From center to outermost it will be C, and this C is equal to 678 divided by 2, and it will yield you 339 millimeter. Again, this distance is known as YB, where flange and web meet, and it equal to C minus thickness of flange. YB is equal to C minus thickness of flange. So you can put the value 339, and thickness of flange is equal to 16.3. So you can put the value 16.3, so it will give you 322.7 millimeter. Again, for principal stresses, you must know the normal stress at this junction. So normal stress at this junction, let this is point B. So stress at point B is equal to YB over C into sigma M. So can put the value 322.7 divided by 339 multiply by 118.19. So it will yield you sigma B is equal to 112.5 megapascal. Now for principal stresses we can use this shear stress as well. So this principal stress sigma 1 or sigma x, I will write principal stress sigma 1 will be equal to, you have normal stress sigma b and bending stress, so sigma 1 is equal to sigma x plus sigma y divided by 2. We have only sigma b, so it will be sigma b divided by 2 plus r is sigma x minus sigma y divided by 2. So sigma x is sigma b, sigma y is equal to 0. So it will be sigma b whole square plus tau of maximum square. So you can put the value sigma b is 112.5 divided by 2 plus 112.5 divided by 2 whole square plus 34.66 whole square. So when you calculate it, this will give you 66.08 megapascal. So this was all about problem 8.5, in which it was asked to select the most economical wide flange for the given loading. So from here we get that we can use 690 W690 by 125 as the beam for this above loading. Then we find out the maximum stress, bending stress and maximum shearing stress. Again at junction of flange and web we have been asked to find the principal stresses, so we need the normal stress at point B as well as shear stress. So we have normal stress and shear stress. So by using the equation for finding the principal stresses, when you put the values, so you will get the principal stresses at the junction of web and flange. I hope this was an interesting problem and you have learned a lot from this. Thank you for watching.